So move ahead with the next problem number 5. So as far as this problem number 5 is considered, we have got with the two different soils, soil A and soil B, which is arranged in a manner as shown in the both the cases, case A and case B. And for all of these two cases, we have been asked to determine the quantity of flow, again the flow rate, which is nothing but and the distribution of the total head with respect to the elevation. So here the elevation at this level is given it as 0, so therefore this becomes a datum. The B interface, the elevation is A to B interface, the elevation is 1.5, and the point A or this particular level is 3 meter elevation, and this particular level is 4 meter elevate. So I'll consider the step-by-step process, and for that the case number A, where the soils are arranged like this, and for case B the soils are arranged in this way, and for case B it is nothing but the tube diameter is given it as 0.75 plus 75, which is nothing but 1.5 meter. The diameter of tube is given it as 1.5 meter. So that, and for the case A the area of flow becomes pi by 4 into 1.5 whole square. But for this particular case, for case B, in plan, half of the tube is made up of the soil A and half of the tube is made up of the soil B. So therefore for this case, area of flow for A plus area of flow for B is nothing but the total area, and obviously the area is divided equally, so half area will be taken by soil A and half area will be contributed to the soil B. So we'll move ahead with the case A. Let's consider. So for the case A, so first of all, it's very important to mark the direction of the flow. See, for this particular phase, if I consider the water level will, if I insert a piezometer, then water level will rise to this particular level, right? This particular level. Even if I insert onto this face anywhere, the water level will rise up to elevation of 4.5 meters. So therefore this becomes the equipotential line. That's what we have seen in our seepage analysis theory. So this becomes equipotential line, and perpendicular to equipotential line there are the flow lines like this. These are the flow lines. But whether the flow is occurring downward or whether the flow is occurring upward, so this is decided by the total head at the interface and the total head at this particular exit phase for the soil B. So for the for this particular exit phase, the total head is nothing but the elevation head plus pressure head. Pressure head over here, the water level is again shown by the triangle and this particular dot. So therefore total head is equals to the datum head plus elevation head. Datum head is 0, and again the pressure head is 0 because water level is not rise to that particular level. So therefore total head at B becomes equal to 0. But why the total head at this particular interface will be elevation head equal to 3 meter plus the water head equal to again 1.5 meter. So the total head will become equal to total 4.5 meter. So therefore it is very easy to calculate, to mark the direction of flow, since total head at this particular phase is greater than the total head at this particular level. So therefore flow will occur downward. Similarly for this case also flow will occur downward. Since the flow is occurring downward, the head will be getting successively lost, and until the water will reach to this particular point, all the head will be dissipated. All the 4.5 meter of head will be dissipated. So therefore if I'm restricting to our discussion to case 1, so I'll again redraw the diagram. So I've got the two different soils like this. So this is soil B and this is soil A, and this is the water levels. This is 4.5 meter elevation, 3 meter, 1.5 meter, and this particular diameter of the tube is given it as 1.5 meter. And after leaving this particular soil B, the water head will be like this, and which has got 0 total head. this is the water head, and this is the water head at the entry face of the soil A, and obviously Ka is given it as 0.1 meter per or 0.1 centimeter per second, and coefficient of permeability for B, it is given it as 0.01 centimeter per second, and they have asked us to calculate the quantity of flow. So remember, in order to calculate the quantity, obviously the formula lies the same, Q equals to KIA, and since there is a head difference, there will be the flow, and you are asked to find out this particular flow rate, the rate at which the flow is occurring. So if I just calculate the total head loss between for all the both two soils, which is nothing but equals to the 4.5, because this is the datum level and this is the total head at A. So 4.5 minus 0, this is the total head loss. So total head loss will be equal to 4.5 meter, which is occurring through all the soil A plus soil B. So therefore soil A head loss plus soil B head loss is nothing but 4.5 meter. I hope you got this particular equation. Head loss, since the water is traveling from this particular end to this particular end, water will go like this, but while traveling this, the head will be getting lost. So once the soil reaches at particular level, the head loss will be equal to HA. So while the water will enter into point soil B, again the head will be lost, right? And the total cumulative head loss after reaching this particular level will be equal to HA plus HB, which is nothing but this level minus this level, which is nothing but the 4.5 meter. So this is the first equation, we got it. But as we are aware of the flow rate, which is nothing but area into velocity, area for the soil A and soil B will remain same. So therefore Q is directly proportional to velocity. And again, since the area is remaining constant, in order to keep the discharge constant, velocity will also remain constant. So therefore VA will be equal to VB. But obviously the Darcy's law is valid in this case also. So therefore V directly proportional to the hydraulic gradient, and therefore V becomes equal to Ki. So Ka into Ia will become equal to Kb into Ib. I'll again repeat what I have done. Discharge which is occurring through all this soil A and soil B will remain same because area is same, and since the area is same and the discharge which is occurring has to be same, so therefore velocity will remain constant. Since the velocity is remaining constant, I just place the velocity in terms of the coefficient of permeability K and the hydraulic gradient I. But while defining the hydraulic gradient I for the soil A is defined as head lost for the soil A divided by length of the soil A divided by LA. For similar, on the same basis, for the hydraulic gradient for soil B is nothing but head loss for soil B divided by length of the soil. Since the length of soil B equals to length of the soil A, Ia will be equal to HA, and LB will be also equal. IB is again becomes equal to HB, because LA and LB are taken it as 1.5 and they are same and will getting cancelled. So I'll rewrite this equation by placing the hydraulic gradient values. So Ka into HA divided by LA will be equal to Kb into HB divided by LB. So therefore we'll get the expression in terms of Ka and HA. Since LA and LB are same, they will be getting cancelled. So therefore Ka by Kb will becomes equal to Ka by Kb becomes equal to HB by HA. Here Ka by Kb becomes equal to HB by HA, right? Here Ka is given it as 0.1, Kb is given it as 0.01. So place this 0.1 and 0.01. So therefore HB equals to 10 HA, or HA will become equal to 0.1 HB. So you'll get this particular expression and you need to place this in the equation number 1. So therefore the HA, which is 0.1 HB, you need to place it in this equation. You'll get HB value which is equal to 4.5 by 1.1 So you'll get it HB equals to 4.5 by 1.1, you'll get 4.091 meter, and therefore HA you will get 4.5 minus of this, you'll get 0.41 meter. So I'll not write 1 over here because it will lead to confusion, because it's 409, so it's 0.41 and it's 4.09. So if you recollect this particular diagram, if I insert a piezometer at this particular end, hopefully the water level in piezometer will rise up to this level, same level, 4.5 meter elevation. But if I insert a piezometer at the point where the soil A and B is meeting, or at the exit face of the A or entry face of the soil B, if I insert a piezometer, then while the water particles are moving through this particular soil, you'll get HA, head loss, equals to 0.41. So therefore 0.41 meter of the total head is lost. So hence the water level will rise up to a level at which this particular level and this particular difference is 0.41 meter. The difference is 0.41 meter, and hopefully at this particular level, so if I just draw the distribution of the total head, the total head at this particular point is 4.5 meter, and this particular point is 3 meter, plus the water elevation level equals to 4.5 meter. But in terms of just the head, the total head at this particular level is nothing but the elevation head 3 meter plus water level equal to 1.5 meter. So total head at this particular level is, I'll write this particular reference, so this is 4.5 meter. Total head at, suppose this is the entry face, at the entry face, this is 4.5 meter, because they have asked us to find it out the distribution of the total head with respect to the elevation. So this is the total head, 4.5, and this will be dissipating it to a 0. So this is a 0 value. So once the soil has moved up to this particular 1.5 meter within a soil A, the head loss will be equal to 0.41. So therefore from total head equal to 4.5, the lost head will be 0.41. So therefore at this particular interface, if I am drawing the head loss, so from this particular point it will go like this, and from this particular offset you will get this particular head loss as 0.41 meter, and the balanced or left out head at this particular level will be 4.09 meter, which is yet to dissipate, and therefore this much particular head will be dissipating in the soil A, and it will again finally reach equal to 0. So the total head at this particular point is 0, because no elevation head, because this is the datum, no elevation head, and water pressure. Obviously if you insert a piezometer except capillary, you will get nothing at this level. So obviously I'll consider the capillary factor to be neglected, so there won't be any rise in the standpipe. So hence you will get equal to 0, and this is the total head distribution diagram. So this finishes the first case, but yeah, the small part is left, that is nothing but the quantity of the water which is flowing across the soil. For that, Q is nothing but KIA. So area for both the case will remain same. I'll write it over here, KAIA into A. Ka is given it as 0.1 centimeter second, so I'll multiply by 10 raised to minus 2 in order to convert it in meter per second, into Ia. Ia will be equals to the head lost for the A, which is nothing but 0.41 meter, divided by length of the A. Length of the A is 1.5 meter, which is equal to length of the soil B, into A, capital A. Capital A is just pi by 4 into d square. The diameter is given it as 1.5. This is the capital A. So you'll place all the values and you'll obviously get the Q equals to 0.1 into 0.41 divided by 1.5, answer into pi by 4 into 1.5 into 1.5. You'll get 4.83 into 10 raised to minus 4 meter cube per second. So we'll get this particular answer, 4.83 into 10 raised to minus 4. Yeah, okay, this is the answer for case A. I will proceed with the case B, which is a interesting case. Only the twist in the case B is the head values. So see, in the case A, we have got the two different soil interfaces, and the flow is occurring like this. So it's the, if you have recollect the stratification problem where the flow is in vertical direction. So the same case, the head will be getting added, the discharge will remain same. But if the flow is like this, which is parallel to the stratification or parallel to beds, then Q will be distributed, but I, that is the head loss per unit length, will remain same. Head loss per unit length will remain same. For the same case is of for the case B, which illustrates that the soil samples are placed parallel to the flow. So this is sample A, this is sample B. Even length is also remaining same, 0 meter, 3 meter, 4.5 meter. Here is the water level over here, and this is the datum. This is the datum. Water while exiting, it will be the same. So this is a very relatively easy case, and if I just reverse this particular paper, the flow will be occurring like this and like this. Since the flow is occurring parallel to the stratification bed, the Q will be divided. So obviously area for A and area for B will remain same, hence flow will be equally divided. Since I'll write it over here, since area for soil sample A, since area for A equals to area for B, the flow will be equally divided. So the total quantity Q will become QA plus QB, which is nothing but Q by 2. Which is becomes equal to, I'll erase, QA becomes equal to QB, which is becomes, the flow is equally divided, which becomes Q by 2, right? Again the same example, Ka becomes coefficient of permeability 0.1 meter per second, centimeter per second, then Kb will be 0.01 centimeter per second. So here Qa will be equals to Ka Ia into area for A, eighth specimen. The total area will be, as you are aware of, total area, A total will be pi by 4 into d square 1.5 square, which is, if you solve this, you will get pi by 4 into 1.5 square, you get 1.767 meter square. So therefore AA will become half of this. So AA will become half of this. So AA for this particular case will become 0.78. So it's 0.88 meter square, and Ka, you are aware of the Ka, you need to calculate the IA. IA is nothing but hydraulic gradient for the soil A. To calculate, in order to calculate IA will be equals to hopefully IB, because if you connect the piezometer at this particular phase, entry phase, and particular this phase, exit phase, you'll get water level up to this level, because no rise in water level except the capillary. So this is the rise in water level, obviously no rise, so therefore elevation head is 0, since, and no elevation head 0, and also no pressure head. The total head at this point is 0. Total head at this particular point is water head equal to 4.5 and elevation head equal to 3 meters. So total head over here will become equal to 4.5 meter, and therefore head lost from top A to top B for HA becomes equal to HB, which is nothing but 4.5 meter. So HA will become equal to HB, which is nothing but 4.5 meter total head loss. Since the length obviously are same, therefore HA will become equal to HB, and also IA will become equal to 4.5 divided by length, which is nothing but 3. We'll get it equal to 1.5. So you need to plunge the value of IA, which is nothing but 1.5. Since as far as the distribution of total head is concerned, along with the elevation, total head at this particular phase will be equal to 4.5 meter, but obviously the IA will remain constant, which indicates the slope of the total head along with the elevation or along with the length of the flow. So it will be 4.5 divided by 3, the slope will be equal to 1.5. With this slope, the head will go on depleting up to 0. So this is the distribution of the total head. There won't be as such any case of the abrupt, because it remains uniform. Slope will remain uniform. That's what it is implicated by I value. So hence only the problem is left out with the total quantity estimation. Since all the parameters are known to you, you can calculate QA equals to 0.1 into 10 raised to minus 2 meter per second into IA 1.5 into AA 0.88. So you will get the answer in meter cube per second, and just you need to take twice of QA, which becomes a total Q. So total Q you will get it in meter cube per second. So from this 0.1 into 1.5 into 0.88, so get 0.132 into 10 raised to minus 2 meter cube per second. So you need to make twice of it, so it became 0.264 into 10 raised to minus 2 meter cube per second. So this actually the finishes your estimation of the total quantity flow for the case B, and also this finishes the fifth problem, which consists of the two cases, and we have also seen the distribution of the total head along with the length of the flow or along with the elevation over here. So we'll move ahead with the next problem, which in which we'll be calculating the effective stress at the different levels of along the length of the flow. In the next problem, number 6, hopefully we'll continue. So this all is the finish. This commences the problem number 5. Thank you.